Hi, welcome to the Calculus 2 lecture series. And we are in the unit number 4. We talk about the sequence and the series. This is our lecture number 18. In this lecture, we're going to talk about the comparison tests. And we're also going to have 2 videos for this lecture. And so the first video, we're going to talk about the comparison test and the limit comparison test. Then the second video is just like similar like we did for the integral test. If by the comparison test, we find a series convergence, then we want to estimate what is the sum of this convergent series. All right, so let's go ahead, go to our lecture notes, and let's go ahead and start here. All right, so like we talk about the key concepts here for this lecture series. So we're going to talk about, so for lecture number 18. So the first is we're going to talk about is a comparison test. Okay, or we're going to, and then we're also going to talk about the limit comparison test. All right. Then the second video we're going to cover is how do I estimate the sum of a convergent series. All right, so the first, let's take a look at what is the comparison test and what is the limit comparison test here. Okay, so for comparison test, first, let's say we have 2 series here. So we have n is equal to an, and we have another series is n to infinity, the bn's here. So both be the series, right, whose terms are all positive. Okay, that means my series is not alternating, like it's not have a positive and negatives here. So the comparison test is will show you, say, if an, okay, if the first series is less than equal to the bn's here, so for all the n's here, all right, so then n the bn converge, then we know what? Then we know the an converges here. So this is kind of intuitively makes sense, right? So if an less than bn, so when the bn converge, that means the bn going to be what? Going to have a sum up to some numbers here. Because it's an is less than bn, so we know an going to be converges as well, right? Okay, so then the next thing is here, if an greater than equal to bn for all the n. And now, if I set n from 1 to infinity, the bn diverge, then we know this existing series n from 1 to infinity an, this one going to be diverged here. So this is also is pretty kind of the the intuitive true. If an is greater than bn, every term is greater than, then the bn add up to the infinity is not converge, then of course an is not going to converge, right? Because every terms of the an is greater than bn here. All right, so the one other thing here is, so for the comparison test, the typical what you want to do is you want to compare to a existing known series, right? So then you compare to the existing known series. So far we know few series we know. So for example, the known series, the first we can compare to the geometric, right? geometric series. So we know how to do geometric series convergence divergence depends on the R. So if the ratio R is less than 1, so we know this one's here. So if this one is less than 1, then we know the geometric series is what is a converge. So this is the known series we can compare to. Then what is the other known series? We know it's the harmonic, right? So the harmonic series, so we know the harmonic series is what? It's a divergent series, right? So it's a divergent series. Then another series we know we call this a P series, right? So the P series, we know if it's a converges, right? So if it's the P greater than 1, then we know this is a convergence here, right? So those are the few series we know is a convergent, divergent, and a certain property. And then we will say is a convergent, divergent by comparing to them. All right, so now what is the limit comparison test here, right? So this one's here, the first one's here, this is just, we call this a comparison test. You just compare to a known series, you know is a divergent or convergence here. Then the limit ones here, so what's that means here? So if I have two series, right? So if I take the limit, so if I say limit n approach to infinity, and then you have this is the an, bn. So if this limit converge to a fixed number, c, and so where, be careful, the c is greater than 0, less than infinity. That means it's a non-zero constants, right? Then we say, then both summation an and the summation bn, they go the same way. So because their limit approach to a ratio, so both a and the b and the either both converge, so it's either both converge or both diverge. So this ones here is also intuitively kind of the truth, right? Because they are running at the same ratios, right? They just running at the same ratio by a constant. So if one converge, the other one, they just difference by a same ratios constants here. Then the one diverge, the other one will diverge. One converge, one other one will converge here. All right, so it's kind of like the intuitive truth here. Then the second one's here. So the second one's here, it will tell you here, right? So if you say the C is here, right? So remember the C here, it has to be greater than zeros, right? How about if I have the AN, BN equal to, how about the limit equal to zeros here? Okay, so if limit equal to 0, that means I know the bottom one is going to go to bigger and the bigger and the bigger than the top ones, right? So now we know if this one's here equal to 0, and now we know if the bn converge, then we know an, then we know an has to converge. This is also kind of intuitively true because when they go to 0, right, that means my what? My BNs here are going to get bigger and bigger, right? So if the BN converge, because this is getting big, and so the AN, well, of course, will be converged otherwise. And because the BN fixed number, then the AN going to, if it's diverge, going to become infinities here, right? So this one is truth here. So this one I should say when better. Okay, so now the next things here, if I say limit n approach to infinity, an and bn is equal to infinities here. So if it's infinity, that means an going to be run a lot faster. So if I know if the Bn, right, if the Bn diverge, then what happens here? Then An has to be what? Has to diverge, right? Right, because in here, like we said, if this is go to infinities here, right? So An going to be going faster than the Bn. So if Bn is divergent now, guaranteed An will be divergent. Right, so the go backward not necessary will be true here. Okay, so now based on these things here, let's take a look here. So remember the few known series we can use to compare, right? Are the what, like we talk about, we have a geometric series, we have a harmonic, we have a P series here, right? Okay, so now let's take a look at here. We want to determine whether those things is converging or diverging by using the comparison test or the limit comparison test here. Okay, so let's take a look here, right? So it's 1 over n squared plus 2n. So remember, right? So we have a P series we can use, we have a geometric series we can use, we have a harmonic. So now in here, this is 1 over n squared plus 2n. All right, so this one here is definitely is less than 1 over n squared, right? Because the denominator is bigger, so it's 1 over n squared. And then I know the summation n from 1 to infinity, 1 over n squared. This is a diverge, this is a converge. Right? Why this is a converge? Because this is a P series with the P equal to what? With P equal to 2. We know when the P series is greater than 1, then it's a converge. And now every term is less than that, right? Less than 1 over 2. So if it's less than, so then I know this one's here, the summation n from 1 to infinity, 1 over n squared by the 2n is a converges here, right? Why? So we will say comparing to a convergent P series. Correct? All right, so be careful. So you always need to give the reason why. So, right, so the reason why you say because I'm comparing to the P series is a convergent P series because P is equal to 2. Okay, now let's take a look at this ones here. So 1 over 2n plus m. Okay, so this looks like we have a good candidate here. This is 2n plus m. I know this one is less than 1 over 2n. That's right, because the denominator is big. Okay, so now if this one is the truth, right? So I know the summation n from 1 to infinity, 1 over 2n. This is a converge. Why? Because this is why? Because this is a geometric. This is a geometric series with what is the R here? With R is equal to 1/2. Because R is equal to 1/2, it's less than 1. So it's a convergent. Okay, so now every number is less than a convergent series. So now I can conclude that n is equal to 1 to infinity, 1 over n plus n. This is what? This is a convergence. Right? So why? Okay, this is because I'm comparing to a convergent geometric. right? So I'm convert. That's by comparing. So you always need to tell the reason why you make the conclusions here. Okay, so now let's take a look at the part C here, all right? So part C, it says summation n from 1 to infinity n the cube roots over the n plus 4, all right? So the n plus 4, so in here, this is a conversion or divergence here, all right? So now in here you say, let's see here. So there are several ways you can show this. So like the first one, I use a comparison. So this is n plus 4, right? So this is n to the cube roots, right? So this one is always going to be greater than 1 over n plus 4, right? So this is always is 1 on plus 4, right? Then what is the summation n plus 4, 1 over n plus 4? So this is for n equal to 1, so it's 1/5, 1/6, and 1/7, right? So I know this is like you just chop off the first 4 terms of a harmonic. So really this is a harmonic series. The harmonic series just have the first 4 terms because a harmonic series is a divergence, right? So it's a divergent series. If you chop off the first 4 terms, doesn't matter, right? Because still it's going to diverge to infinity. So that's why now you have the everything is a greaterness, right? So now I can conclude that this n equal to 1 to infinity. So this is n to the cube, n plus 4. This is divergent, right? Why? Because I'm comparing to a harmonic series. I know the harmonic series is a divergent series, right? So so I know that's why I know it's the harmonic series. So let's take a look. We have another way we can do that. If you don't think you can, you don't want to use a harmonic, let's do this one here. Then you said, okay, well, I get another series that will define the summation n from 1 to infinity bn. Let me define this like this way. Right, so let me define that this is 1 over, let's see here. This is the 1 over n to the square to the cube roots. All right, I can define this one. Okay, so this one's here. Let's see here. This is n from 1 to infinity, 1 over n to the 3/2. This is what? This is a divergent. Why? It's because this is the P series, right? So this is a P series with I'm sorry here, I wrote down the wrong. So this will be, so this is cube roots, right? So it's 2 to the 3rd with P equal to 2/3 is less than 1. So I know it's a divergent because this P series is a convergent, is greater than 1, right? So this is less than 1. Okay, so now I know this is a divergence. Now let's take a look at my using the limit test. Let's see how that works. So this is an, bn, right? So I will say this is a limit n approach to infinity. What is my ans here? An is n plus 4. Then this is n to the what? N to the cube, right? And now the bottoms here, this one's here, this is 1 over, like this is the n to the what? 2/3. Okay, so now you say the limit n approach to infinity. So this is n to the 1/3. This is n plus 4 times this is n to the you flipped it, right? So this is n to the 2/3 and to the 1. So this will be limit n approach to infinity. So 2/3, 1/3, this is n plus 1. What is n plus 1? It's 1, right? So I know by limit test, so you can say the other things here. So you say, hey, summation n from 1 to infinity, n plus 4, n to the cube. This is divergence, right? Why? You will say by limit comparison test, right? So you will say that by the limits comparison test, right? So you can have a different way. So you say that by limit comparison test, or you can just like we say here, you can say, hey, by comparing to a harmonic. There's no definite way, which way is right way, which way is wrong way, right? So you have many different ways you can prove it's a divergence or convergence here. Okay, now let's take a look at the concept ones here. So they said, suppose A and B are positive sequence. So it's a low situation, it's a sometime, always, or never. So we say if the limit an over bn approach to 0, that means we know the bn going to go faster, right? Then if an converge, do I guarantee bn converge? Wow, this one here is what? This one is sometime, right? So if the BN converges, right? So we know if the BN converges, then AN definitely converge because this is go to 0. BN is go faster. And so BN, the rate change is faster. So if BN converge, then the AN converge. But the reverse is AN converge, is BN convergent sometime. So you say, why you say sometime? I can give you an example. So for example, right? So for example, see here, if you let the AN is equal to 1 over n to the cube, right? Then the BN is equal to 1 over, I'm sorry, AN, let's do this n to the square, right? Then the BN is 1 over n, right? So the AN over BN, so you say the limit n approach to infinity, AN over BN is will be what? It's 1 over n, so will be equal to 0, right? But I know AN is converge, this one is converge is okay, right? Because this is a P series, right? So this is a converge. But unfortunately, this one is not a converge, right? BN is not a converge. So this is what? This is a divergence, right? Why? Because this is a harmonic. So that's why the answers for this ones here we say is sometimes, all right? Okay, so now let's take a look at B's here. So the B is just like we just wrote it before. So if limit n approach to infinity, an over bn is equal to infinity. So the infinities here, that means what? That means the an go a lot faster. Even is faster than Bn. So if Bn converge, then Bn diverge, then the An is diverge. So is this always true? Yes, this is always true, right? Because in here is going to the infinity, that means, you know, the An going to be a lot faster, right? So if Bn you diverge, then An is faster than Bn. So of course, An is diverges. All right, that's it for this first video. We talk about the comparison test and the limit comparison test. So the second half of the second video about this lecture series is just like similar like we did for the integral test. If I prove a series is convergent, I want to estimate what is this series converging to? What is the estimation for the sum? All right, that's it. Okay, so let's talk to you on our second video, how to find and estimate the sum of a convergent series. All right, have a good day. Okay, bye-bye.